All right, well, why don't we get started? So, thanks everybody for being here. Those of you in the room in person, and I know there's several people out on Zoom. Hopefully this will go smoothly. Usually in these Forum for AI speaker series, I'm often the one who introduces the speaker. But this time I am the speaker, so I'll take a minute or two to introduce myself before diving into the talk. I am Peter Stone. I'm faculty here at UT Austin and have been for longer than I can remember now, about 20 years, I guess. I'm also executive director of Sony AI America, and it's my work at Sony that I'm going to be talking about today. I know there's some visitors here on campus today, some prospective grad students, and there's people on Zoom who are not from here. So I'll just take a minute to talk about some really exciting things happening here at UT Austin. We do have now, we got one of the first NSF institutes, AI institutes, the Institute for Foundations of Machine Learning, and use that to found the machine learning laboratory that's directed by Adam Clivens and Alex Demakis and several other people involved. And I'm a member of that. I'm also a founding member of our sort of AI for Good initiative here called Good Systems, a bridging barriers initiative that involves faculty in computer science engineering, but also in social science, humanities, very cross-disciplinary, bringing together humanists and technologists, thinking about what does it mean for an AI system to be good. And there's going to be a Good Systems symposium in 2 weeks that'll also be publicly available if people would like to come and hear about the work going on there. And then the other hat I wear on campus is I am the director of Texas Robotics. And for those of you who haven't seen it yet, we have a beautiful new space, the Anahist Gymnasium just down the street. We'll be hosting the main robotics conference, ICRA 2025. So in 3 years, there's many of my colleagues here are across multiple departments focusing on robotics here at UT. But just as when I give a one-slide introduction to myself and my research, this is the research question that sort of ties all of my research together. It's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? My research group and I publish in several different sub-areas of artificial intelligence, as shown here. And most relevant to this talk are the areas of reinforcement learning, and to some extent multi-agent systems, and robotics. We work on both fundamental sort of new theory and algorithms for AI, and also more application-driven research. Some of the applications that have motivated my research over the years are the ongoing robot soccer competitions. I'm the president of the RoboCup Federation, and this is what some of the robot soccer competitions look like these days, where the robots are fully autonomous. I also work on general purpose service robots, so robots like this one. This is joint work with Ray, who's in the room, where we have robots like this one wandering in the hallways, learning to do multiple different human interactive things, including grounded language learning. And autonomous traffic. I had a car in the DARPA Urban Challenge back in 2017. But today I'm going to talk about sort of one of my most recent projects that was done, as I said, at Sony AI with a bunch of colleagues. It's a project that was recently published in Nature, and we landed on the cover of Nature, which we're very proud of, and there's some beautiful artwork on it. So I have a nice poster of this in my office now. But really that we think of as being a landmark result in artificial intelligence, sort of in the series of results of computers being able to beat the best human champions at various tasks, such as chess and Go and Jeopardy and poker and sort of various tasks like this. We haven't yet achieved the RoboCup goal, which is by the year 2050, creating a team of humanoid robots that can beat the best World Cup soccer players on a real soccer field. But this is sort of, I think, in that series this is a part of that progression. And when we started this project, we didn't know if it was going to be possible. It was still thought that human drivers were much better at high-speed racing than autonomous drivers. And we were able to show that that's not the case now. This is a large collaborative project over the course of a couple of years. The first author on the paper is my colleague, Pete Werman, who is best known for having invented the Amazon robots. He was a part of Kiva Systems. He was at Amazon Robotics before joining us at first at Cogitai and now at Sony AI, and many other people here, including 3 alumni from PhD alumni from UT that got their PhDs here in my lab. You can see them on this slide: Sam Barrett, Piyush Khandelwal, and Patrick McAlpine. So some of you who have been around at UT will recognize them and their names. And also many other fantastic reinforcement learning and AI folks on this team. So the mission at Sony AI has been to unleash human imagination and creativity with AI. The aim is to advance artificial intelligence so that it augments and works in harmony with humans to benefit society. It was established a couple of years ago with a remote workforce here in North America, offices in Tokyo and Zurich. And we have 4 flagship projects. We've been working on imaging and sensing, sort of robotics kinds of things. We have an AI ethics flagship that's really gathering some steam, had some nice results recently. AI for gastronomy, food preparation, and helping with high-end chefs. And then the one that I'm going to be talking about today is AI for gaming. And this article in Nature was sort of the first sort of reveal of what we've been working on in this AI for gaming flagship. And so, as I mentioned, we did have this this article published in Nature. And as with all sort of these AI landmarks that I mentioned, winning at Go, winning at chess, this is sort of a similar kind of theme where there's a lot of engineering behind it, trying to put together the best computation we can, the best algorithms that are existing, and then also a few sort of special new innovations that we had to do to get us over the top. And so I'll try to highlight in this talk both the engineering efforts and those sort of new contributions, the new algorithms, the new techniques that we put together. They're also highlighted in the Nature article if you want more details on it. So the task we set out to do was to beat the best drivers in Gran Turismo, which is a very popular PlayStation video game. It's a very real driving simulator, and it's actually incredibly impressive. I wasn't a Gran Turismo player before I started this, but it's the physics that are modeled in this game, for those of you who aren't familiar, are incredibly real, from friction to airflow, slipstream, sort of tire slip, downforce, and traction. It's all there, and it is used by professional drivers. There's people who have started racing in Gran Turismo who've gone on to become professional race car drivers, and there is a esports competition in Gran Turismo. So there are real bona fide human experts at this task, people who have devoted a good part of their life to becoming experts at this task. And so we identified 4 of the best humans in the world, as shown here, and we identified 3 tracks that we wanted to compete with them on. And these are, again, real tracks that real race car drivers drive on as well. The Dragon Trail Seaside, we used a Mercedes class car. The Lake Maggiore, a Porsche, and then the famous Cirque de la Sarthe, which is where the 24-hour Le Mans happens, with very high-speed F1 cars that go at hundreds of kilometers an hour. And the race format that we decided on was 4 of our autonomous cars, GT Sophy, against these 4 humans, and then in each race, you would get points for what place you finished. 10 points for finishing first, 8 points for finishing second, and then 6, 5, 4, 3, 2, 1 points for finishing 3rd through 8th in the race. And because Sarthe is more complex, the points were doubled for that one. And we held 2 races, one in July, in which the humans did a little bit better than the GT Sophy. So we lost that race by points, but then went back to the drawing board and repeated in October, and were able to handily beat these same 4 drivers. And I'll talk about sort of what made that possible throughout this talk. So one of the advantages of working for a company that also makes movies is you get nice features like this. So I'll let you hear this.
There's very few places where you can go out and say, I'm going to build an AI, and I'm going to make it truly superhuman.
This will give you a sense of what the setup was for the race days.
going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo Sophy is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
このなんか車文化、車という存在をもう丸ごとビデオゲームの中にこう再現したいなと思った
This
ん
is the
ですね。
inventor of the Gran Turismo series. And
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophy agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースしていきたいなっていうふうに思いましたね。
there is on the GT Sophy website, there's a 10-minute version of this video, and then they're also now working on making a much more extensive feature of sort of the making of Gran Turismo. But now I'll tell you some of the technical details that went into training GT Sophy. So at the top level, it is a reinforcement learning agent. I think this is actually important. I think conventional wisdom before we started this project was that race car driving was really something that's best done by model predictive control, by a model-based kind of approach. And instead, we set out to do this with model-free reinforcement learning. And importantly, it's through an interface. The AI agent was not inside the PlayStation, was not sort of a part of the game, but rather was just getting sensations from the game and sending actions to the game, the same way that the person has to do that same sort of thing. And so, the standard RL diagram here, where there is, actions being sent, throttle, steering, and brakes. We're getting state. I'll tell you more about the state and the reward. And tried to do it as much as possible with the same kind of state information and action interface that people have. As I said, a big part of this was the engineering and the compute infrastructure that went into it. To train GT Sophy, we partnered with Sony Interactive Entertainment along with Polyphony Digital, who makes the game, to build a modern reinforcement learning training platform with thousands of PlayStations that were used to sort of as the rollout workers to get data of what happens when in a particular state you send a particular action. That data was collected in an experience replay buffer in the sort of standard reinforcement learning method these days. And then we used a new algorithm that we devised, which is a variant of soft actor critic or SAC called QRSAC, which I'll talk about again in some detail in this talk. And that's sort of one of the sort of innovations that we needed to be able to get over the top here. Compared to some of the other AI challenges in the past, there were sort of three distinguishing features in GT Sophy in this challenge. One is sort of that you have to operate at the edge of control. It's high-speed control in real time. And if the car goes a little bit faster, it's going to spin out. If it goes a little slower, you lose all your advantage. So you need a control policy that's going to be right on that sort of razor-thin edge of optimal control. Secondly, and that's even just on an empty racing track with no other cars. Then when you get into having other cars around, this actually was a surprisingly difficult aspect of the challenge, that you can have a car that's really fast on an empty track, but the professional human drivers are still going to be able to beat it easily because they're better at the tactics, when to pass, how to block those passes, those kinds of things. So figuring out how to get those tactics involved into the control policy was important. And also there's this really interesting ill-defined aspect of etiquette. When people are racing, there's a human steward, a human judge that decides whether moves are fair or not, and there's no real well-defined rules of what's fair. You're not allowed to cut off another car or force them off the track. So you want to go as fast as you can, but without cutting off anybody. Everyone has to have their line that they can drive on, and so trying to work that kind of notion of sportsmanship into the agent without being too timid was also a big challenge. And I'll talk about how we addressed all of these as I go forward. So first, the interface, the features, the actions, and the rewards given to the agents. So the state that was given was the 3D acceleration, velocity, and incline of the car. 3D because some of these tracks do go uphill and downhill. So you get the incline and where you are. The most recent actions that were sent, the tire load and the tire slip, and also the position and orientation along the course, and a 3D representation of upcoming track points. So like here's what the course looks like, and we would give like a how far around the track you are, and also points here in 3D. If the car is here, it would get sort of the points of what the right, left, and middle of the track are for an upcoming segment. And then the actions were taken at 10 hertz, so 10 times a second, along 2 dimensions, pressing the throttle or pressing the brake, and also the steering angle, so a simple action interface. And then the rewards, and this is the rewards for the empty track. I'll talk about what happens when there's multiple cars in a few slides. But reward for making progress along the course, a penalty for going off the course, or for hitting the wall, or for slipping too much. And then we did some in the Nature article. There's some ablations. Our baseline, we could go around one of the tracks in 114.47 seconds. I'll talk about how good that is later. If we only use the course points, but as the input representation, it would do more than a second slower. If we only use a different representation, it would do even worse. And if we just use the projected position where you are on the track, it didn't do very well at all. And then we also looked at what happens if we get rid of the off-course penalty. That would decrease performance significantly. And if we just used a fixed time step cost, which is the sort of naive way to do reinforcement learning in this, it wouldn't even finish. It never learned. So we needed curating the reward function was important. Yeah.
So how hard are those features to get from the image representation?
So these there was an API created from the game that would give these features. And it's there are things that like you could argue that maybe the tire load, tire slip, those numbers aren't given to a human driver. On the other hand, there's things on the visual interface that a human sees that is not given to the car. So they're not identical. It's hard to give exactly identical interface unless we learn purely from vision, which we didn't do in this case. That would be an interesting future challenge. But we did try to make it so that roughly the same amount of information was coming. Yeah, good question. Okay, so I said one of the innovations, and this part of the talk gets a little bit technical, but then I'll jump back out to results for people who don't follow this. But we introduced a new algorithm, which is basically you can think of as a distributional reinforcement learning algorithm. So rather than just modeling the expected reward of an action or the expected return of an action, it would model the whole distribution of possible outcomes. This is a method introduced, I think, by Mark Bellamere and colleagues, and it's been sort of people have been experimenting with in the community. But we did it in a particularly in a new way that turned out to make a difference. Interestingly, the agent was still selecting its action based on the one with the highest expected reward. So, or its highest expected return. So it was, we're still trying to figure out exactly what is the advantage of doing the full distributional modeling. It could be that it's an auxiliary task in some sense that makes the neural network more robust. There are other possible explanations, but I'll show the result. It definitely using this QRSAC compared to just soft actor critic did make a significant difference in terms of the results. But what it basically does is it modeled. We used 2 networks and used the sort of in the same method that double DQN does, and use the minimum value of the 2 to avoid overestimation bias. And the neural network is outputting not just the expected value of an action, but the sort of 32 bins of what of the possible expected rewards. And again, for those of you interested in the technical details, there's more in the full details in the Nature article. We're using a Huber loss function on those buckets. But again, I said the policy objective itself is just using expected value. So if we and we also used n-step returns, so a little bit of hybrid between one-step returns, full TD and Monte Carlo. I'll talk a bit. You'll see the importance of that. But here's the algorithm of using the results of using QRSAC versus SAC for learning in terms of time around the track. And then also if we change the amount of bootstrapping or amount of sort of how far ahead you look in the future to sum the rewards. It looked like in the July race we used 5-step bootstrapping. After doing this result, we actually changed to 7-step bootstrapping for the October race. And this helped smooth the reward signal on the high frequency actions. Again, it's a slide of technical detail, the neural network training details. 4 hidden layers with feed-forward networks with 2048 ReLU nodes. The hardware was important. We had a lot of GPUs and CPUs being used here. We used it was important to use mini batches, and smaller batches than 1,000 would actually significantly degraded performance. Having a dropout on the network also sort of allowed to stabilize or remember skills, not forget them, or be more robust to some of the skills that the car needs to learn. I'll talk about those skills later. Oops. And there was asymmetric learning rates for the critic and for the actor, which again is a method. The target network being stabilizes a little bit, and using clipped gradients was really important, because if a car drives off the track, that would have a huge negative gradient. We wanted to not let that affect learning too much. Okay, so that was probably the most technically dense slides of the talk. This is now showing some of the results. And this is again on an empty track, which we call time trial. This is on a bank of 10. The blue lines here are the 100 best times by human drivers on Kudos Prime, which is sort of the public repository where people log their best times in this game. And then using a bank of 10 PlayStations with 20 cars per PlayStation to gather experience for the replay buffer. After 4 hours, we're getting times that are not human competitive yet. After 8 hours, close to the built-in AI that comes with the game, and after 24 hours, doing close to better than any other human has on this particular track, which was Maggiore. On the other 2 tracks, Seaside and Sartre, we did better than any human was able to register. This is showing the orange is the distribution of GT Sophy's 100 best lap times, or 100 lap times, not best, but 100 lap times on this Maggiore, and then these are the means of the 5 best humans. So there's only one that's able to sort of be in the mix with GT Sophy, and again, on the other 2 tracks, no human was able to get within a few seconds of GT Sophy. And here's what it looks like on an empty track. You'll notice on that razor edge, it's actually going closer to the walls than people probably would. But it's really driving at high speed and high precision. Just at the degree that it's allowed. And drive very, very precisely. So one question that you might ask is, where does the AI do better? And we asked, where does the AI do better in the track? And so this is on a particular track on I believe this was on Sartre, and here's where you can see the distribution of Sophy's times compared to the 5 best human drivers on this track. And we raced against a professional driver, Igor Fraga, and this is when I run this video actually.
We don't have the same precision.
I need to put it at high resolution so you can see there's a ghost, which is, so Igor Fraga is racing against GT Sophy. GT Sophy is the ghost in the front. You'll barely be able to see it on the screen. And this graph is showing sort of his time behind GT Sophy over the course of a lap. And you can see the places on the track indicated here where the car gained time on him. And you can hear him talking over this a little bit.
So it gets way more difficult to do the same things, and they can react like very, very quickly. Man, that's fast. That's really fast. Like I really want to watch the onboard as well to see how like they throttle and braking trace, steering trace as well. It works because This is definitely something else.
What he's asking for there is to see sort of the telemetry data. What actions was Sophy taking at a given time? And so we plotted that for him, and that's what you'll see on this slide. On the top is the steering, where the blue is him, Igor, and the red is the orange is GT Sophy. So you can see that the human is a lot smoother, and then this is showing the throttle and the brake. And if you look at this graph, people thought actually maybe that the AI would learn to brake later than humans, but actually it turns out that that if you look at this carefully, the GT Sophy is learning to brake a little earlier than the human, but then is able to accelerate more quickly. And so here we have him comment.
I think there was a lot from the AI driving that I could take to myself, and maybe with some twist, I think I can adapt something to myself as well. So it was like very, very interesting.
So a couple of questions we sometimes get is, was this fair from the perspective of perception modeling, right? A person sees the screen and can't react instantaneously. And so in the Nature article, we did do an ablation study where we artificially delayed the perceptions from the video game to GT Sophy by 100, 200, or 250 milliseconds, and the human reaction time in this game is about 250 milliseconds, and found that we were still able to reach superhuman performance even with those delays on the empty track. We didn't try it in the versus mode. The other is that people were acting continually, so more smoothly, and also used manual shifting. So whereas GT Sophy was using automatic gear shift, which is actually a disadvantage. It's more complicated to use the gear shift, but it gives you a little extra action fidelity. And so even without that, even with using automatic, we were still able to do well. Yeah, question.
Yeah. So we also do an ablation study where you made some of the non-human features more noisy. Like for example, the tire sip and so on, right? You could imagine that humans can figure it out from looking at it, but it's not as good as actually getting it, right? And so you can make that noisy. Was that something like that study?
Yeah, we have not done that so far, but that's something we could easily do. That would be interesting. At least as far as I can recall, we haven't done that. Another question that sometimes comes up in this game is at this point in the talk is and this is a little bit related to that, but not exactly your question, but is the game deterministic or not? And most of the game itself is almost deterministic, but we're interacting over a network, so it's asynchronous. So that's why we get a distribution of possible outcomes. But yeah, that doesn't answer your question. The noisy features, and this is true, like compared to real race car driving, that's one of the perception on a real car out in the real world would be is one of the big challenges. And so yeah, that's a good future work direction. And so, but I don't have results to report right now.
Peter, we have a few questions from Zoom. Would people like to unmute and ask?
Yeah, if somebody wants to ask, now's a great time. I don't see the chats on my computer, but I guess I wonder if I can. Yeah, why I'll if anybody wants to unmute, go for it. Or if a colleague or friendly member wants to, if somebody in the room has it up, if somebody wants to read to me any questions that are relevant, then I'll try to answer them. But I'll go on. Please do feel free to interrupt. I'd love to answer the questions that are on there. Yeah.
Hi, Peter. This is Ben on Zoom. I had a question about your observation about the early braking. Has that led to a change in strategy? I mean, we've heard similar things with players in poker and Go making use of AI to adapt their strategy to win. Have you seen any changes like that that's come out of the implementation of Sophy?
Interviews we did with the drivers after the fact, and some of them are saying that this might be, that they are learning some things a little bit from the way GT Sophy, that it's changing their way of thinking of it. And this idea of driving, with a ghost of GT Sophy in front of you is something that they're really interested in doing to try to change their strategies in some ways like this. So yeah, this is starting to happen now, and I'll talk about at the end of the talk that it's sort of a goal for us to be able to roll this out there in the game so people can experiment with those kinds of things. But yeah, anecdotally, the professional drivers are saying that they are getting ideas from watching GT Sophy. Yeah.
So what's the training data? Is it trained on the single map for 24 hours, or it's trained on collection of maps?
So the training was separate for each of the different map and car combinations. So
do you have an idea about a few shot learning setting where you transfer to some new map?
yeah, and so clearly to roll this out into the game, it'll have to do well with all of the car track combinations that are possible, and that's something that we are working on, and it seems to be feasible to do. But in this particular, for the purpose of this talk, each training was done specifically for each of the different tracks. Yeah.
So this is more game related, but so it seems like the best drivers have like a rig. It's not just some little handheld controller, but it's like they've got the steering wheel, and
that's right.
Do you need that to be competitive in the game?
Yeah, if you're a human, as a human driver, you want to be sitting in the console with a steering wheel, with the brake and pedal. If you can play the game with just a PlayStation controller, that's what my kids do at home. And yeah, it's okay, but you're not going to get to the professional level of it. At least that's my understanding. Again, I'm not personally a GT expert. I do quite poorly. But you know, my kids are getting respect. All right, yeah.
So the previous slide you had shown like the throttle and brake inputs, right?
Yeah.
So it seemed like the AI one was like very discrete. Is
Yeah.
that something humans could do? Like,
I don't think that's an advantage. I think well, so there is an advantage possible is that you can jump from one setting to another. So you see some discrete jumps like this. But it's moving at 10 hertz. So you can only change actions 23 to 30 milliseconds, whereas the person is acting continually. So I don't think a person would want to, unsmooth, to change to discrete actions like this. And a person really wouldn't be able to do that. You imagine, moving an action every tenth of a second. This is, we did this mainly we thought this was roughly the rate at which people were acting, but in fact, people are acting more smoothly.
You attribute all the changes, whereas a human is going smoothly and Sophy is going, all this up and down. That is checking for possible goodness of those decisions.
Yeah. Well, not checking. It's a fixed policy when it's not learning while it's racing. In this case, it learns. All the training was done, and then we have a fixed policy for the actual race. But it could be that it's like, I'm in a danger, like, this is a danger moment, and I need to, I'm at a risk of collision, and we see some examples of that it's changing. Yeah, Alex.
From Zoom,
Yeah.
people are saying if you can repeat the questions.
Okay. Yeah. I will do that. So the latest question. Okay, I thought that Mike was picking things up, but I guess not. Yeah. So I was answering some questions about how smoothly GT Sophy works, and whether in this case it was checking the sort of the discontinuities here. We're checking for different actions. Yeah.
Another question. You may have spoken about this, but did you take the model that you developed and the policy and so forth, and then apply it to new tracks where you hadn't trained? Right.
So the question is, and this was a similar question earlier, could you take the policy and apply it to a new track? We have done that, and it does fairly well. But yeah, again, in this talk, everything is on training for a particular track. And we also recently are looking at, can we move, this is all done in GT Sport. There's a new version of the game, GT7, and so we're looking to see whether the policies will transfer to there as well. Good, let me move on. I'll be happy to answer more questions as time permits at the end. But let me move on to this. I've got sort of two other segments of the talk, training with opponents and then some of the race results. So first of all, I mentioned this notion of sportsmanship that's important, where you have to have etiquette. You can't be too aggressive. And here's what happens. You'll see here, GT Sophy is the gray car when it's too aggressive. That's aggressive agent. On the other hand, in this one, I'll show this timid agent where the announcer, as the race was going on, says GT Sophy has a lead over the human, and it looks like a commanding lead. It's not going to be easy to pass. And then the person does pass. And we had, in a race analysis afterwards, we were able to look at it from a different angle down here and see that Sophy put on the brakes. Presumably the judgment was that if I keep moving forwards, yes, I'll stay in front, but there's too much of a risk of collision. And so it was too timid. So here you'll see This was from the July.
And he's ahead then of Tomoaki Yamanaka as they come in towards Indianapolis. So it's the Sophy AI system ahead of Tomoaki Yamanaka. So it's Miyazono from AI, from Yamanaka from AI, from Kokuman from AI, from Ryu from AI. So it is very, very interesting, and this is proving to be a very exciting climax to the race. And it's going to make things very interesting in terms of the overall point standings then here as well. We come through our nose. That was the last real overtaking opportunity then for Sophie Orange. But is Yamanaka going to try and invent something down into the Porsche curves? You bet he is. What a move then from Tomoaki Yamanaka to get it ahead. Orange runs it a bit wide through that.
So that was a pass, and it was that that the agent was too timid. It wasn't doing this balancing, etiquette, and nerve well, and so we added into the reward function a series of sort of penalties for collisions. One, you get a penalty if there's any kind of collision, regardless of whose fault it was. Higher penalties for rear end collisions, that's clearly your fault. And then we tried to also sort of add some penalty terms for sort of heuristics of whether it was your fault or not, or when it wasn't clearly the opponent's fault. I'll talk about how those made a difference. In fact, yeah, it was in the full racing reward function, we did tune these weights a little bit for each of the 3 tracks. And so the black was sort of the nominal, but then when we went to SART, we put less of a penalty for going off course. We made it linear instead of squared, because you're going really high speed and you have to sort of get really close to the edge of the track. And so we penalized the car less during training for going off the track. Again, some of the maneuvers in this at high speed required tire slips, so we zeroed out the tire slip penalty. And then in Maggiore, it starts in a grid where all the cars are near each other, and so there tends to be very close maneuvering, so we reduced the collision penalty there because there do tend to be some bumping. And then in SART, we upped the sportsmanlike penalty to try to avoid avoid sort of being too aggressive. And this, so these are notions where we did need to do some human engineering to this, right? So there's, and I'll talk about another as we go, but curating the reward function was important to success. So now in the head-to-head kind of case, what we did is we gathered data from some full track scenarios, so you could put 20 cars, on an empty track. That's what I've already discussed. But then we also created some scenarios where we start GT Sophy in red behind either 1, 2, 3, or 7 other cars. And we also created some experiences for particular difficult parts, like the grid start on Maggiore, or some straightaways where it could learn to do slipstream passing, which is an important technique where you get in the air resistance of the car, the flow behind another car where there's less air resistance, get extra momentum and sort of bounce out and use your extra momentum to pass them. And so we did that in particular segments, and there's a particularly difficult chicane. And then we also did that for these other tracks where we tried to gather data that would be important for the agent to learn about. And then this was another really key aspect, is we curated the experience replay buffer for the learning agent. So this shows basically on one of the tracks on Maggiore, starting from 0, going up to the end, where at the beginning of the track up to 13, which is the end of the track. We had different mixes of these different types of experiences. So, the grid start was important at the beginning of the track. The final chicane was important at the end of the track. So the experiences in the experience replay buffer have, what position the car is in, and then, sort of data from these various scenarios that are color coded here. And then, and so that gave us sort of a mixed experience replay buffer in these different proportions. And then importantly, we did stratified sampling from this experience replay buffer so that when the agent would actually get the right mix of experience. If we just did, if we created a replay buffer that looked like this at this point of the track and then just sampled randomly, it would get, there would be sampling bias and it would get too much of one experience versus the other. So we enforced that it had exactly the right mix while it was in each of its mini batches during training. And then we can, we did some ablations. So here's, first of all, an example of a slipstream pass that I talked about. for that. A PID opponent was one that we made either go to the right of the track or the left of the track, so you could learn to slipstream pass on either side. If we took that out, we did a little worse. If we didn't use the slipstream scenarios, we did significantly worse. If we just used one table, experience replay buffer, instead of having this stratified sampling, we did a whole lot worse. This is in terms of team points, like, that where I said 10 for winning, 8 for second, that kind of thing. So this is, in team points how you do. If we didn't give the passing reward, we did worse. I think I might have skipped a slide. Let me see if I. No, oh yeah, I did. This one I didn't tell you about this very important slide, which is the opponent representation and passing rewards. So to represent the opponents, we had two lists: the cars in front and the cars behind. So GT Sophy's the green car. In this scenario, it would say it would get the relative position, velocity, and acceleration of the cars in front in a list here, and the cars behind as shown here. And then there was a reward term added for overtaking or gaining ground on a car in front of it, or a negative reward if the car within a range gained ground on you. And so this was important for being able to do the multi-card stuff. Yeah.
So in this case, are the opponents just like AI, or are they like humans?
So the question is, who are the opponents? I'll get to that. Whether there's just the built-in AI, that makes a difference, and I'll get to that shortly.
And then my question is, the API gives to Sophy this information about all the other cars?
Yes. So the question was, does the API give to Sophy the position of these other cars? And yes, we basically the API we could get out from that where the other cars were. We did a lot of experimentation with what this. It doesn't give it in this representation. It gives, we can extract through the API where all the other cars are. And we experimented with sort of radial representations of how many cars are in different cones and stuff like that. This turned out to be the best, the one that worked best. And I think we have some data on that in the Nature article about how the different representations did. Okay, yeah, I don't know how I skipped over that slide, but let me go back to where I was. Yeah, and I talked through this slide already. Okay, so to answer the question about who did we train against, so. The agents that we trained against were a mixture of some built-in AIs, the ones that exist in the game right now. They're sort of slow and very courteous. They're not very aggressive. A few line follower agents, these sort of PID agents that I talked about that just stay to the right or left of the track, and then some other Sophy policies which tend to be fairly aggressive. And oops, jumping a little bit. So the blue dots here are the baseline. It shows the 4v4 team score, which you want to be to the right as much as possible, and the number of sort of questionable collisions the agent was involved in. So here we find in the end it was able to be not involved in many collisions and do well. If it trained just against the built-in AI, then it ended up being very aggressive. It would get sort of pretty high team score, but would have a lot of collisions. If it went only trained against aggressive opponents, it learned to be very cautious, not very many collisions, but it didn't do as well in score. So we needed to have this mix. And in the end, you can see this sort of nice... appropriately being aggressive, but not cutting off. Very, very high speed and close. Now, when we did the races, we had the sort of the nerve-wracking task of which of the trained agents should we play against the people, right? We've trained with lots of different policies, and so we went through we created a fairly large pipeline for training the agents, a whole bunch of different agents, filtering them to make sure they had a certain set of properties, like they could do slipstream passing and stuff like that. And then we created sort of an N-athlon, or we called like a decathlon, where test in a whole bunch of scenarios. Does it is it too timid? Does it do slipstream passing? Can it get around the chicane fast enough? The ones that would pass that, we then did 4v4 races to see how they were in competitive mode. Then we tried a couple of human tests against a professional driver that we were working with, and then we picked the best one to deploy against the set of 4 professional drivers in the actual race. And it was important to do this. We couldn't just take the agent that was trained at the end of a trial and assume it was best, because we would see that it would sort of learn and unlearn skills. Like on this slipstream test, various different agents, even the best one, the baseline one, would learn it, but then, unlearn it for a little while as it was training, and then, relearn it and these kinds of things. So we had to make sure that all the properties we wanted were in the policies before we did the final results. Okay, and then to get to the race results, I'll show you some of the things that were eventually learned. So in the July race, we actually found that we weren't aggressive enough at the starts, and that's when we added these sort of start tests for, especially in the one race in Maggiore, at Seaside, where there's this grid start. You can see there's, if I play it,
followed by Cockerman and Violette. They're all darting into the slipstream to try and get a run on their fellow competitor. Only Bordeaux does not have the advantage then of that slipstream. Into the braking zone of turn 2 we go. It's a lunge from Cockerman as he tries to go up the inside, but it's actually Sophy Violette who goes on the outside into turn 2. Very aggressive driving then from Violette and up into second position at the end of the first corner. So it's now the two GT AIs that are in.
So even right at the start, we sort of got out to an advantage on that one. And then here's a nice little...
At the exit of the corner and on the run down in towards turn 17. Could an opportunity present itself then here for Ver? Well, going defensive then is Yamanaka. Ver goes towards the outside. This is getting pretty close between them as they run side by side into turn 17. Yamanaka holds firm in the inside line, and Ver is not able to get themselves past them and through and up into fourth position for the time being. So over the timeline we go. This is where the slipstream though of course will help Sophy Ver as they come down towards turn 1 and then into the braking zone of turn 2. You can see the lift off the throttle there for Ver is just don't want to get too close behind coming through those series of corners. Big old bit of opposite lock as we come down the inside. Miyazono's trying to go through there as well, but not close enough. Ver goes through on Tomoaki Yamanaka though for P4, so aggressive and robust driving from the AI then as they move themselves up a position.
Was the commentary automatically generated, or
No, those were human.
Was that real time, or were they?
Yeah. So the question was the commentary automatically generated? No, that was so. It was in real time. There were people. So I mean, I would have been at this event if it weren't for COVID protocols. It was done in a studio at the game studio, Prolific Digital in Japan. But the people from the Tokyo team were there. The racers were there in the building, and there were some announcers that were commenting on the races.
They sound professional. They sound very professional.
Yeah, and then if you watch some of the Gran Turismo professional esports events, the same kind of thing happens. There's professional commentators.
Would it be cool to have automated commentary for the players of the game or something?
So the question is, could they do automated commentary for this game? And maybe, yeah, that would be a great challenge for the natural language processing.
Worked on this for RoboCup.
Yeah, that's right. That would be a great thing to for NLP people to focus on. Here's another. Yeah.
What's the in-game AI like?
The in-game AI, the built-in AI, is fairly timid. It's one that's it's okay, but even non-experts, like I can pass the built-in AI. It's not very challenging. It just sort of provides cars on the track. I mean, there's different modes of it, but it's for expert drivers. It's not any competition at all. Yeah.
Is there teamwork involved in this game?
So the question is there teamwork involved in this game? There's not supposed to be. In the July race, it seemed like we weren't sure whether the people were sort of teaming up a little bit. To help each other. The GT Sophy agents were completely unaware of which cars were human drivers and which were other GT drivers, so they did not have any notion of that. And in fact, in the July race, we did see our cars sort of interfering with each other a little bit. And by the October race, actually, this clip I'm going to show here.
In the bench we go. That's where we saw Yamanaka making a bit of a hatch of it last time around. As a result, he now sits down in 7th place. Through the tunnel we go. Again, very close to the wall on the outside. Violette, they're just lifting off the throttle ever so slightly. Bit of dust being kicked up by Bordeaux under the braking zone. Does that cost them a bit of time on the entry? It certainly does. Cost them to run wide and miss the apex by half a metre or so, I should say. And now Violette's got a good run as they come on towards the start-finish straight. Has to dart back, though, into the slipstream as we start the final lap of race 1 for race.
For these races, the people were told not to collude, and the agents weren't able to collude. Yeah.
There's a comment on Zoom that when you play the video, the audio of the video is much louder, and they can't hear your voice when you're just Just FYI.
Okay, yeah, I'm sorry for those of you on Zoom that it's.
Just maybe you can lower. I don't know if you can lower.
But then we can't hear it.
But then it'll be hard to hear.
But it's computer generated.
You can't win.
I'll go in between a little bit. Yeah.
So going back to selecting the policies, have you ever tested if one policy was very good at one skill and then one policy was very good at another skill, but could you switch the policies in real time depending on what
Good question. So question was, could we learn a policy, have a policy that was really good at one thing, and then another policy that was good at another thing, and could you switch them? We actually did do that for the July race. We had like a policy that specialized at starts, and then we would move to a policy that would be for the rest of the track. By the October race, we got everything distilled into a single network. And when you do that switching, then it raises all kinds of questions, like when should you switch? And can you switch smoothly? It was messy doing that. But in principle, we could have done that. It was a goal for us to get everything, all of the knowledge distilled into a single network. And we were able to do that by the October race. But good question. Jody.
So have you by any chance seen any impact on how the human racers race, if whether or not they're told that they're racing against an AI agent?
I see. So the question is, do people race differently if they know they're racing against an AI agent versus against people? We haven't done that study. I'll give some driver testimonials. Maybe you'll get a little bit of that at the end if you hold on. But yeah, I can't answer that definitively. Just a couple more slides, and I'll take any more questions people have. And I apologize for those of you on Zoom about the noise, the volume balance. I can't do too much about it. But here are three clips from the same part of the track. Where the first one is the car driving on its own. The second is a car with one opponent where it just stays to the outside and doesn't pass, and then another where it does this outside-in maneuver, all in the same part of the track, but it's doing it differently because there's different opponents. I'll show you those yellow. Here is it drives differently depending on the opponents, and this is actually a really good example of that. There's sort of a particular turn where the red line is what GT Sophy would do if there were no opponents, and then the green and the gray are what GT Sophy actually did against two human drivers. And you'll see that they sort of allow them to they both get passed, or they get passed by the people, but end up in a position where it's more advantageous, and they're able to end up in front by the end. Those are sort of the kinds of the tactics, and then finally, I think this might be the last clip. In that same place where I showed you earlier, the same part of the track in Sartre, where we thought Sophy had the lead, and the commentator said, "Oh, it looks like you're going to win," and then the person passed. Almost that same place in Sartre, this time in the October race. That was from the July race. In the October race, Sophy ends up passing the lead human and staying ahead for the rest of the race. So successfully stopped being so timid in that kind of a scenario. Okay, final results. In July 2nd, as I said, that's shown in the right column here, the humans barely did win. Actually, GT Sophy did well in the first two tracks. Well, actually, sort of, I think humans won in Seaside and in Sartre. GT Sophy won in Maggiore. Overall was 70 to 86 in favor of the humans. Because of some of these issues that I talked about, that being timid and those kinds of things. By October, when we fixed everything, to the best of our ability, GT Sophy won really convincingly. First and second in every race, never finishing worse than sixth. And here you sort of see on each of those tracks the time behind the leader of all the various cars, and when they got, so you can we can see when they got passed and stuff like that. A few driver testimonials, which you can read here. Tomoaki Yamanaka after a particular pass, and then two other professionals when they were racing against GT Sophy in time trial mode. Here's Emily Jones talking about her experiences.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in.
Sorry,
and
it's probably too loud there, but the people in the room can't hear it otherwise.
It was really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learnt a lot about the lines, and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me to the next corner. So I didn't notice that until I saw the AI, and I was like, oh, okay, cool, I should do that instead.
Good, and I think that's basically the end. I just have one slide on some upcoming challenges. This is there's ongoing work here. Obviously, I sort of alluded to this already. The obvious question is, can we productize this? Can we put it into the used in the game? We're working with Polyphony Digital on possibly putting it into a future update of GT7. To do that, it has to be able to work on all the different tracks and track car combinations. We have to make sure that it can work with on a PlayStation rather than on sort of external computers. And you don't want to just the goal is to make the game more fun, so it shouldn't just be an opponent that beats you every time. You want to have it at sort of different levels. Maybe it could be a teacher, maybe it could be a teammate. There's all kinds of different possibilities here. There's other things we didn't address, like tire wear, and then having to go to pit stops. That's a part of human races in this, and different weather conditions. There's other racing challenges that are still open challenges. We could do opponent modeling, as was alluded to by one of the questions, or more strategic decision making. So far, there is no opponent modeling going on. Explainability and interpretability of GT Sophy's behavior would make it more useful for helping experts get better. As again alluded to in some of your questions. And we are identifying now, the degree to which each of our insights, like things like QR SAC and curating the experience replay buffer in the way we did, how general those are, and whether they will help in other domains. We're working on submissions to the standard AI conferences like NeurIPS and Coral and ICML and things like that. So watch for future details that'll answer some of the questions you have here as we continue our investigations in this domain. And we are at Sony AI working on, like I said, this and other tasks with the idea of creating AI systems that help unleash human imagination and creativity. So with that, I'm just about out of time, but I'm happy to stay around if there are questions. I thank everybody for your attention. If there's Alex, if there are others on Zoom, feel free to let me know. Yeah, please.
Just a quick off the wall question. From your observations, do you think that the competition would be different if the humans would not have sound available to them?
So the question was, would the competition be different if humans didn't have sound available to them? The agent did not get any of the sound. I have no idea. That's a great question. We could try that experiment. Yeah.
Yeah, so I saw in your model that you augmented the state space with the past actions taken by the car. Can you talk a little bit about the intuition behind doing that and whether that might be applicable to other RL problems?
Yeah, so the question is, why did we give the agent past actions? Why did it matter to know what it was doing and why in the past? The intuition behind that is that if you're in a braking maneuver, you might you don't want to change your mind and brake and then accelerate and then brake and then accelerate. You probably want to have some consistency if you're acting at 10 hertz so that there's some kind of hysteresis in your actions. So we want the agent to figure that out for itself. I don't know if we've ever, I think these features were things we found were necessary as we were going informally, but I don't know if we have any ablation on that. But that's it's a good question.
Do you think doing RL is crucial to achieving superhuman performance because current self-driving models are all using IL?
Yeah. So the question is do I think reinforcement learning is crucial to getting superhuman performance, given that many self-driving models are using imitation learning or using model predictive control also is the other thing that people do here. It's hard to say. We are checking to see, we are looking at some model predictive control approaches as well here. We haven't optimized them quite as much as the RL yet, so it's hard to say definitively whether another approach could work or couldn't. One of the things we found is that MPC is pretty good at an empty track, but when you get to this notion of having to integrate the both fast driving with the tactics, being able to do that all into a single distilled neural network seems to be advantageous. And then with regards to imitation learning, it's not clear that that might speed up training, but it's not clear that humans you want to imitate people. It might be the reverse, that people might want to imitate what the RL has learned, because the RL is learning to do things a little differently. So yeah, I think actually in the end, using this model-free reinforcement learning approach was crucial to getting this result.
Hey, Peter.
Yeah.
This is Michael Roberts from Hypergiant. To follow up on that policy switching question, what about trying an ensemble of Sophys running in parallel?
Yeah, so could we run an ensemble of Sophys running in parallel? And we'd still have to have, then you'd have to have some sort of action selection or disambiguation method, right? So
Like
at
maybe
any
a
given
blending.
time, there's one car being controlled. So if there's an ensemble of controllers, you still have to do that orchestration of which one is going to get control now. I think
Right. But you could maybe blend the control responses, and then I could imagine even having an RL model on top of the other RL models.
Yeah.
That was just blending. In other words, and then that might more resemble the human brain's response, and it might smooth out the control output.
Yeah, I mean, ensemble methods are well, explored in AI, and it's possible that that could have a difference here, make a difference here. That policy switching, I mean, again, I think it adds extra layers of complication. That our goal was to try to get this all into a single network, and we were able to do that. So, but yeah, I mean, could it make things work better? Possibly. There's all kinds of this is sort of a point, right? We can describe the solution that we were able to use to get to superhuman performance. It doesn't mean it's the only possible solution. And so yeah, that would be worth exploring as well. Yeah.
Great.
Have you ever considered trying to match the features that humans use with the features that Sophy uses, using both just the vision input, maybe also some accelerometer input because humans can actually feel acceleration.
Right.
Using sound as well, and just trying to mimic exactly what humans.
Right. So the question is, have we tried giving GT Sophy exactly the same or as close as possible the same interface that people give? Learning the most obvious way to do that would be to learn just from the visual signal, maybe also the sound signal, something like that. I mean that's something that we've thought about and explored, and it's something that we may still come back to. That we made a decision early on in the project to focus on this interface and try to make it as close as possible to what the humans are doing, but not to go straight from vision, which is sort of the next computational challenge. So again, that might be something that we still come back to, but so far we haven't. I can't say that wouldn't work. We haven't given it nearly as much effort as we have this approach.
With the core stuff that you've learned, what else? What are and I'm sorry I haven't read the article, but what other domains or problems do you think now that would be useful for?
Right. So the question is, what other domains would these things be useful for? So I mean, QRSAC is a very general algorithm, and just distributional reinforcement learning. I think that there are many situations where that can, when there's sort of when there's risk, when you need to be sort of risk aware in some ways, and when you want to be on this sort of edge, thin edge of what we call the razor thin edge of not too fast so that you lose control, not too slow so you lose your advantage. I think this distributional method and some of the particular ways that we used the distributional reinforcement learning, I think, is a very general method. And I think this curating the experience replay buffer as well. And these are some things we're focusing on. A domain that I think this is actually very related to, which we work on in my lab here at UT Austin, is social navigation. So imagine a robot trying to move through, and this is in collaboration with some other people in the room here. But like imagine a robot trying to move through a crowd, like after a football game or something like that. Same thing. The robot wants to do what it needs to do, follow its own line, but it needs to be aware of where the people are going. It's not nearly as the high speed that we're dealing with here, but it's, I think, similar kinds of issues. And so, I think there's possible lessons learned from this that could apply to sort of robot control in multi robot scenarios, even in lower speeds.
Hi, Peter. There's a few questions on Zoom. The first one is, would this work for robo race?
Okay, yeah, so it would be a fascinating challenge to get this working on real cars. It's something we haven't tried. There's some difficulties that first of all, getting all this training data. I mean, when it's learning here in RL, it does crash and run into the wall and things like that during training, and we get millions of examples, and so doing that in the physical world would be difficult. We'd have to address the sim to real challenge. Also, the perceptual noise, as was alluded to earlier, would be different. It would be fascinating. It's not what this project didn't set out to do, that to get this working on real cars. Our goal was to be better than the best human drivers at Gran Turismo. And I don't want to make any claims as to whether this would win it on real cars. I think that's a different challenge.
Right. The next question is it possible to let the AI vehicles work together to get better results? And what would happen if two groups of AI vehicles were competing with one another?
Okay, so great question. So I think if you put the AI, if you let the AI agents collude and know about each other and try to optimize their team score, I mean, at the very extreme, one car could sacrifice itself and just crash all the humans, get a huge penalty, and the other three win, right? So that wouldn't be very interesting. I mean, I think that it's possible. It could be, and it's something that would try. What happens if we race groups of AI agents against each other? That's what we did as a part of our training pipeline. I'm going to lose battery on my laptop shortly, but I think that's okay. I can keep talking. But in the in this training pipeline, that's what this PvP bullet zone was, where the agent was trying to, where we played 4 GT Sophys controlled by the same program against another 4 controlled by another program, and see which ones do best. So we had a lot of experience on that, and that's fine. That works out as you would expect. Some of them do better than others. That's all.
Great, thanks. And then the last question from Zoom is, did you try to limit the change of braking power or steering between 2 cycles to a human comparable level? From the graphs, it looked like that the AI could change both within 10 ms at will.
Yeah, so we have not tried. We've not tried, enforcing sort of smoothness in those values. That would be something that we could try. But again, the human is smooth in different ways. Or can change in different ways that had an advantage. So that would be another experiment that we could try. I'm not sure how much of an effect that would have. Any other questions?
It's another of the wall question. How do you forget?
Yeah.
In the world of day trading stocks and with computer software, if you think of the different stocks as they move in price, as competing cars running against each other, and you're trying to get ahead. Can you see any way of applying some of your techniques there?
Yeah. So the question was, could any of these techniques apply to stock trading? There's a history of people in reinforcement learning trying to apply reinforcement learning to stock trading, and there's been some methods with different success. The ones that are most successful, of course, don't publish. Instead, make a lot of money. But yeah, reinforcement learning in general can apply to some financial problems. I don't know if there's anything specific about GT Sophy that would transfer over there, but RL in general is potentially applicable. Yeah.
Is your state space finite, or is it a finite state space problem?
The question is the state space finite? That's a good question. So technically, no, I think that the incline. Where did I had the state space right here? the accelerations, velocity, and incline. I mean, it's on a digital computer, so finite technically. I think you can think of it for all intents and purposes as continuous, though. I mean, it's like, you know, the XYZ accelerations and the, you know, the points in space. The version of the position along the course was actually passed through a sine and cosine function. So no, the inputs are continuous along many of the dimensions.
Hi, Peter. There's only time for one more question, and there's one question on Zoom. Kirby, can you unmute, please?
Yep, can you hear me?
Yeah.
Great talk. I had a question about the racing etiquette aspect. You mentioned that it's quite ill-defined, and there's even humans who are in charge of deciding what actions are within etiquette or not. I'm curious to what extent you consider the etiquette problem solved, and if your well-trained agents still act in surprising ways that could be considered outside of racing etiquette.
Yeah, I don't think we consider this problem, any aspect of this problem, solved. And I think there's still fascinating questions, like I alluded to on the last slide, which I can't change to anymore because my laptop battery died. But you'll recall, like, there's things like the pit strategies and different weather and generalizing to different tracks and things like that. And yeah, I think the sportsmanship aspect of this also is not fully solved. And there's still, yeah, we still when we run agents and we see what they do, we still see surprising things, and we're still learning. And we still are getting experiences from human drivers playing against them. So in racing, and we expect a lot more of that to happen in the future as we continue working on this. So anyway, there is another talk in this room about to start. So I need to stop here. Thank everybody for your attention. And I do, if you want more details, I invite you to to look at the Nature article. It's all written in there.